Okay, so Mr. Kadwaru here again, and what we're going to be looking at today is one of the past CSEC moments questions. It's from 2005, paper 3, question 4. And we're going to look at a simple method of basically um, answering some of these moments questions. So this is a method that I would have developed over time. I think it's very simple. It just involves drawing a line and putting in the relevant information, and I think once you get to that point you will start seeing the solution in front of you. It's very difficult to just read a question sometimes and be able to visualize, and that's why it's very, very important that we draw a diagram that can show us all the pertinent information such that we can make a proper analysis and answer the question. So the question starts by saying, with the aid of a labeled diagram, describe an experiment to determine the center of gravity of an irregularly shaped piece of cardboard. Of course, you already know how to do this from our previous video and from our classes, so I'm sure you can answer that and get the full 8 marks that has been awarded in this question. The next part of the question is what we're going to look at now. So the question says, figure 3 shows a bicycle of mass 15 kg resting in a vertical position with the front and back wheels touching the horizontal ground at points P and Q respectively. So let's first of all figure out what we just read. We were given the mass of the bicycle. So this bicycle has a mass of 15 kg. So therefore its weight should be 150 newtons. W equals m by g, mass by gravity. 15 kilograms by 10 newtons per kilogram, which is of course accepted by CSEC, is 150 newtons. So the weight of this bicycle, right, is 150 newtons, and it is standing vertically, right, and touching 2 points P and Q on a horizontal ground. So the ground is horizontal, the bicycle is standing vertically, and its wheels are touching at points P and Q. So that's the information that has been given thus far. So let's look at the diagram. Now I want you to forgive the crudity of the diagram that I drew on the board. I was never really good at art. In fact, I never really passed art, to be quite honest with you. This is the diagram. I tried to replicate it as best as I can, but it will serve our purpose. Now, first of all, in your diagram, what you will see is that the wheels are touching at points P and Q, and there are 2 upward forces. At Q, there's an upward force R2, and at P, there's another upward force R1, right? These forces are very aptly or correctly named R standing in this case for the word reaction. It's short for the word reaction. So when the wheels touch the ground, they get an equal and opposite reaction from the ground, right? So, and that reaction of course is R1 and R2. So those are reaction forces. When we get to Newton's laws and we look at the third law, this will make a little more sense. But for now, I'm telling you that forces R1 and R2 are reaction forces. The reaction, of course, when the bicycle wheels touch the ground. Okay? Another piece of information was also given. The distance PO. Now, O happens to be the point where the center of gravity, the line of the center of gravity, the line through which the center, or the weight of that object seems to act, is that line comes down vertically like that. So of course we can say that there's a force acting downwards here, and that force is the weight of the bicycle, which is 150 newtons. And we know we can put the weight there because we know at the center of gravity, that's the point through which all the weight of the object seems to act. So now basically we have the distance PO. we have been told in the question that the distance PQ happens to be 1 meter. So we fill it into the diagram here, 1.0 meters, right? And of course, if this entire distance is 1.0 meters, and this distance here is 0.3 meters, then the distance from Q to O will be 0.7 meters. Yeah? Alright? So that's basically what the information that we've been given today. Now the question asks, given that the normal reactions of the ground on the front and rear wheels are R1 and R2 respectively, write two equations in R1 and R2 which satisfy the conditions for equilibrium. So they're asking you now to use the two conditions for equilibrium that we discussed in a previous video to basically write two equations in R1 and R2, meaning that both equations must have R1 and R2 in them, all right, for the equations to be valid. So we have to use those two conditions of equilibrium. If we remember correctly, the conditions for equilibrium are the principle of moments, which states that for a system in equilibrium, the sum of the anti-clockwise moments is equal to the clockwise moments about that same fixed point. And of course, the sum of the forces in one direction is equal to the sum of the forces in the opposite direction. So we're going to use those two conditions, right, to write two equations that must have reaction forces R1 and R2 in them. Okay? So the best way to go about doing this is to first of all draw a line. So we draw a line that represents this entire system here. A line seems to be a lot easier to do. Okay? And we put in points P, points Q, points P and Q. So this is point P here, and this is point Q here. At point P, of course, we have a reaction force going upwards, that's R1. And at point Q, we have a reaction force going upwards, that's R2. Let's put in point O. Point O is somewhere about here. And we know at point O, the center of gravity, the line of the center of gravity is acting through that point. So therefore, the weight of the bicycle, which is 150 newtons, we know is at point O, because that's where the center of gravity is, at point O. And of course, the center of gravity is the point through which all the weight of an object seems to act. Alright? So the thing is, we now have something looking like a seesaw here. And the seesaw is very easy to look at, and you can figure out what is balancing, which force is balancing the other. Now, what we seem to not have here, of course, what we've been familiar so far with, is a pivot. And, well, in moments questions, now an object can pivot about many points. In fact, an object can pivot about point Q, point P, and in this case, it can pivot about point O. Alright? So wherever forces are acting, an object can pivot at that point. Now, most objects, of course, sometimes the most suitable place for the pivot is at the center of gravity. Okay? So, in order for us to, of course, observe a turning effect, there must be a pivot, right? And there must be forces causing clockwise and anti-clockwise moments. So we have to choose, of course, where are we going to put this pivot. And in this case, the most ideal place to put the pivot would be basically here. Right? So I'm just going to kind of put in a imaginary type pivot here so that you could, see that this object is pivoting about its center of gravity. Right? Now, what happens in this case is that if we were to place that pivot here, and we can't do that, we can say that this object is turning about this point here. We now cancel basically the effect of the weight, right? Because we're now, if we are saying that we have a pivot here, then that weight is being supported and of course that weight is now cancelled. Alright? The effect of that, or the turning effect in this case of that force is now nil. So basically that's what we have. So if we now look at this situation, it seems now that we have something looking like this. R1, upward force, R2, upward force, and of course we have a pivot here now. Okay? And so therefore if you think about it, this distance being, as we know, from P to O was of course 0.3 meters, and from O to Q, or Q to O, was 0.7 meters, and I got that only because of course the entire distance from P to Q was 1 meter. Then if this is pivoting or turning about this point, then R1 is going to cause, if R1 is pulling upward, it's going to cause this system to rotate clockwise, and R2 is going to cause this system to rotate in an anti-clockwise manner. Right? So clockwise movements being caused by R1 and anti-clockwise movements being caused by R2. So R2 gives you that anti-clockwise turning effect. R1 gives you the clockwise turning effect. So what will be an equation that will give us, of course, equilibrium, that satisfies the condition for equilibrium? And we know the principle of moment says the sum of the anti-clockwise moments is equal to the sum of the clockwise moments. So that, and we have to write an equation. So what is causing the clockwise moments would be R1, right? So I'll just erase this here. It will be R1 multiplied by a distance of 0.3 meters must be equal, that's the distance away from where we are pivoting, we're choosing the center of gravity as our pivot, right? Must be equal to R2 multiplied by 0.7 meters. And this is the principle of moments. These R1 is providing clockwise moments, so this is the sum of clockwise moments here. Moments. On this side, this is the sum of the anti-clockwise moments. Alright, so far so good. So we use one of the conditions of equilibrium, which is that of the principle of moments, and we came up with this equation, R1, which is the clockwise moments, multiplied by 0.3, force by distance. R1 is the force, this is the distance, R2 is the force, this is the distance, and we came up with the first condition for equilibrium. Now, there's another condition for equilibrium, and of course that is upward forces equals, or not upward, but forces in one direction equal forces in the opposite direction. So if you look at this diagram again, we will also end up with a situation where we have something looking like this. We have R2 going upwards, R1 going upwards, and the weight of the bicycle, W, which is 150 newtons. Alright, let me just put in the weight here so that we know that this is the weight of the bicycle, right? So these are two forces going upwards, R1 and R2, and one force going downwards from the opposite direction, which is the weight. So forces in one direction equal forces in the opposite direction. So the other equation would be R1 plus R2 equals 150 newtons. Or it could have been R1 plus R2 is equal to W. W, of course, being the weight, which is 150 newtons. So the two conditions for equilibrium, of course, principle of moments, sum of anti-clockwise equals sum of clockwise for a system in equilibrium, or sum of the forces in one direction equals the sum of the forces in the opposite direction. And in this case, the two upward forces will be equal to the downward forces for this bicycle to remain in equilibrium. Remember, this bicycle is in equilibrium. It is standing. It's standing vertically. It's not going anywhere. So it certainly is in equilibrium. And therefore, that means that the upward forces, in this case the reaction forces from the ground, is equal to the weight of the bicycle. So the bicycle stays in one place, right? It is in equilibrium. And of course, the turning effect that can be provided by the both reaction forces R1 and R2 are also equal, and therefore the bicycle remains in equilibrium. So I hope this clears up how we take these two conditions for equilibrium and we apply it. And very often what we have to do is draw a simple line, put in the forces, and we start just seeing this kind of seesaw, and we can figure out now, okay, if this force pulls this way, I get an anti-clockwise. If this force pulls this way or acts this way, I get a clockwise. And we can figure out very simply how that system is going to behave. So I hope this helps, and I'll see you in another video.